So the title is Astrochemistry and the Making of Habitable Worlds. And there are two reasons that this is a topic that fascinates me. One is illustrated by the image on this first slide. You know, it's our home. It's a habitable world. So to try to understand our own origins, how we went from a dead world to a chemically rich world to a biological world. So it's the first big question. The second is that we now know that we are just one planet among many. We belong to one solar system among many. If we look up on the night sky, we now know that pretty much every star that we see has its own planetary system. So the second question that I find fascinating is trying to understand how often we can expect these systems to also be living or habitable worlds. And this is a project that's ongoing. It's one of the big things going on in astronomy is characterizing these planets around other stars. And what we are finding is that these planets and planetary systems really come in all shapes and sizes. So this is an artist's impression of a small fraction of the exoplanets, the planets around other stars that have been discovered to date. And the main thing I just want to have as a takeaway is that there are all kinds of planets out there. Some of them resemble planets that we find in our own solar system, so small rocky planets, gas giants, ice giants. But actually the most common planet that we find is something in between. In the media, it would be called either a super Earth or a mini Neptune, dependent on if they want to focus on the potential habitability of that planet or not. So we want to understand, as said, our own origins and also how often we can expect some of these these exoplanets to have their own origins of life on them. Now we have several different sort of roads towards answering that question, which is just what's illustrated here. If we want to understand exoplanets and how often they would be chemically conducive to having life on them, the most obvious thing to do would be to go and study those exoplanets, to try to figure out, do they have water, do they have oxygen, do they have organics, that are things that we think either are needed for an origins of life or are signs of having life there currently. Of course, if we want to understand our own origins, then looking carefully at our own solar system seems like a good idea. And especially there are bodies in our own solar system that are quite pristine, that should tell us what the solar system was like when it was very, very young. These are the comets. They are very cold, small bodies that have been stored in sort of the outer parts of the solar system and for billions of years, and therefore haven't changed that much for those billions of years, and should maintain a record of what the solar system was like when the Earth was forming. Now, where I will be spending most of my talk, and I'll try to motivate why in the coming slides, is in the study of the birth environments of planets. So both our solar system and the exoplanetary systems that we see, we think they all basically form the same way. And they formed in disks around young stars. So when stars are between 1 million and a few million years old, they are surrounded by disks of gas and dust. This is where planets form. And the idea is that by studying the planets sort of as they are assembling, by studying the material that these planets are assembling from, we can learn things both about our own origins and how often we can expect exoplanets to have a similar origin to ourselves. So let's start with exoplanets. So what can we learn from the direct study of exoplanets? Well, so most of the thousands of exoplanets that have been discovered by now are discovered by through the so-called transit technique. So all this means is that we observe the star. As the planet passes in between us and the star, we see a slight dip in the light coming from the star, and that tells us that there is a planet orbiting the star. But you can learn much more from this kind of observations. In particular, if you look at the same star and look at the dip at different colors or wavelengths, and you see differences in sort of the dip size, that can tell you what these planets are made of, at least what their atmospheres are made of. And through these studies, we have learned quite a bit about the number of exoplanets. So this is one of the more beautiful so-called spectra that have been acquired of an exoplanet. So what's shown on the x-axis is just the wavelength or color, and then on the y-axis is the transit depth. So if you have a planet, it's going to block out a certain amount of light from the stars it passes in front. If you have, for example, some water in the atmosphere, and you look at a wavelength where water particularly absorbs light, that planet is going to appear bigger at those particular wavelengths. So that's where you get this sort of wavy pattern here as you look at the sort of size of the planet at different wavelengths. The main takeaway is that we can see that there's water in this planet. That's something that we can observe when we observe exoplanets. Now, this particular planet is about a Neptune-sized planet that's orbiting very close to its star. Has an orbital period of just a few days. That would be much closer than Mercury in our solar system. Now, if we're thinking about habitable planets, these are not the planets that we are the most interested in. Rather, the planets we're interested in are smaller planets that are orbiting further away from their stars. So astronomers talk about the planets we're being interested in sitting in the habitable zones, or sometimes you hear they talk about temperate planets. So all this means is that planets that are sitting at a certain distance from their star, they have the right temperature to sustain liquid water. That's all that's meant with a habitable zone. So if you're sitting at an orbit at just around a solar type, like a star like our sun, at an orbit that's just a few days, you're going to be too hot to be able to sustain liquid water. If you're sitting too far out, let's say beyond Mars's orbit, you're going to be too cold. Water is always going to be in the form of ice. So we think that to have life that is anything like what we have here on Earth, you need to have water present, and therefore astronomers have defined this habitable zone as the same as the sort of liquid water zone. Now, where this habitable zone falls around the star depends on the star. So if you have a small star, it's dimmer, this zone is going to be closer. If you have a brighter star, this zone is going to be further away. So taking this into account, and also the hypothesis that you need some surface around to have the kind of chemistry that we think can lead to an origins of life, had led to astronomers designating on the order of 10 to 20 planets as candidate habitable planets. So this is just what this artist's impression shows. So these are all sort of Earth-sized planets, roughly. They're rocky, and they're sitting at this right spot around their star to be able to sustain liquid water. So these are the planets that we would like to acquire spectra of to see what is the chemistry that's going on these planets. Now, in theory, this would be possible, and this would be an excellent way to find out if these are living planets. If we take the kind of spectra that I showed of the previous Neptune-sized exoplanet, of the terrestrial planets here in the solar system, we would see very substantial differences in the colors or spectra of Venus, Earth, and Mars. And this, in theory, we could do of exoplanets as well. The problem is that this is currently not technically feasible. I don't know if you remember a few slides ago, the spectra I showed of this Neptune-sized planet that's sitting very close to its star. It was not the beautiful spectra like these. Taking spectra of Earth-sized planets that are much, much further away from their star is currently just not possible, at least not with the kind of detail that we would need. If I were to come back in 5 to 10 years and give this same talk, I have high hopes that I would be saying something different. There are a couple of telescopes being built both for space-based research and for ground-based observations that are there to address exactly this question. The James Webb Space Telescope is on its way. One of the things that will allow us to do is to look at much smaller planets further away and acquire these spectra. But right now, in 2018, we're just going to have to put that to the side. We're not going to learn that much about exoplanets and their chemical habitability from studying their atmospheres directly. So we'll come back to then what we can learn about their formation zones. But first, let's just have a look at the solar system and what we could learn about our own origins by studying the solar system. So this is one of my favorite images of the Earth. So Earth is here. So this is an image by Cassini, this space mission that flew to Saturn and spent a lot of time characterizing Saturn and its moons. And it's looking at Earth through the rings of Saturn. So putting exoplanets aside for a moment, what can we learn about our own origins by just studying the solar system? Well, even a rather cursory look will actually teach us quite a bit. And particularly, there are sort of three things in this title: that the Earth was formed in a disk rich in water and organic molecules that we can learn just by, I said, a pretty cursory look at the solar system. So let's start with the first one, a disk. This is that the Earth and the other planets originated in a disk of material around our sun is a rather old realization. People have known for a long time that the planets orbit the sun in what's almost a perfect plane. That was something even the ancients realized. And as early as in the sort of 17th, 18th century, dependent on, if you're Swedish, you would say it was Swedenborg who was first. If you're German, Kant. There's some other candidates as well who first wrote down that this meant that the planets probably formed in a disk around the sun. But they are in a disk, and the most natural explanation is that they formed in a disk. So the second two claims they're making is that we can tell that these planets, our solar system, formed in an environment that was rich in water and organic molecules. So water first. The solar system is very rich in water. When we look at the Earth, that makes sense. We have a lot of water here. I mean, Mars seems pretty dry, maybe. But if you just take another step outward and you start looking at the giant planets and their moons, if you look at comets, if you look at the Kuiper belt, they are just very rich in water. The Earth is water poor in comparison. One example, my favorite example, is one of Saturn's less well-known moons, Enceladus. So if you've heard about Saturn's moons, you've probably heard about Titan, the giant moon of Saturn. This is a much smaller moon, but it has a special interest among scientists thinking about life elsewhere, because this moon has a big plume of water that's spewing out into the solar system. This was discovered by Cassini, and I mean the plume is almost as big as the moon itself. And the reason it has this plume is that it has an underground ocean of water. This is basically a water moon. And as I said, this is not unique. Water is very common in the solar system. The third final thing is that we formed an environment that was rich in organic. Oh, actually, before getting that, there's one more place where we have a lot of water, and where you actually can learn something about where the water comes from, is in comets. So comets, I think most of you have probably heard that the tail of the comets comes from basically water and dust evaporating off the comet as it gets close to the sun. Now, if you look at the water closed in comets, and actually everywhere else in the solar system where we see it, you will find something rather peculiar. You'll find that there's a lot of heavy water around. So heavy water just means that you have replaced one of the hydrogen atoms with a deuterium atom that has twice the mass of a hydrogen atom. Now, this doesn't really change how the water appears in the comets very much, but spectroscopically we can tell them apart. So we can measure the percentage of heavy water in these comets. And as I said, there's a surprising amount of it, much more than you would expect if you just took the amount of hydrogen and the amount of deuterium that you have in the cosmos. Now, this is something this is a clue to where this water came from. And there's some very basic physics you can use to have this to get this clue. So all molecules vibrate. molecules always vibrate a bit, and that gives them a sort of ground state energy that they cannot not be below. Now, these vibrations depend on, like, the energy of such a vibration depends on two things. One is basically the strength of the bond or the spring in this vibration, and the other are the masses that are attached to this spring. So if you double the mass attached by changing the hydrogen to deuterium, you will change the energy of this molecule. And you'll change in such a way that the heavy water has a lower energy state than the normal water and is therefore favored basically by the universe. I mean, in some sense, if you think about any system in the universe, it's trying to go do two things at the same time. It's trying to minimize its energy, it's trying to maximize its disorder or entropy. So in this case, if you want to minimize the energy, you produce more heavy water than normal water. So that's now, but this difference in energy is very, very small. So if you're sitting at room temperature, like we're here now, that energy difference is just so small that entropy is going to determine what you do, and you're going to make normal water and heavy water just as easily. But if you are down at, let's say, 10 degrees above absolute zero, even this small energy difference matters a lot. And the reason that we see this excess of heavy water in comets, and actually also in the Earth's ocean, is because this water formed very cold. The water that we have in the solar system formed at temperatures below 30 degrees above absolute zero or so. So it's very, very low temperatures. And that actually tells us where it formed. It did not form close to the sun. It formed either far away or long ago. Those are basically the two options. Most likely the water that we have here on Earth is older than the solar system itself. So we have a lot of water. It's, as I said, prevalent throughout the solar system, and it probably predates the solar system in terms of age. Now, the final thing I said was that we formed an environment that's rich in organic molecules. Now, obviously, if we look on Earth, we have a lot of organic molecules. You know, it's what all life is made of. But here, life has really contaminated the original chemistry. You can't really learn that much about the original conditions on Earth by looking at the present-day composition of Earth. But as I said, there are comets. These comets preserve the initial composition of the solar system. And if you look at what these comets are made of, you see that it's mostly water and things like C and CO2, but then there are a lot of organic molecules as well. And I've tried to scale the size of these molecules, so the area scales for the percentage in the comet. It's roughly correct. What you should take away is that if you add up all the organic molecules in a comet, you get that about 10% or so of the comets are made up of these small organic molecules. So, knowing some about our own origins, it's very natural then to ask that all those exoplanets that we know of, those potentially habitable planets or temperate planets, how often did they form in the same kind of environments with those ingredients that we associate with being conducive to an origins of life? And here I think, by the way, it's nice to just pause and sort of question the statements that I've just made, that water and small organic molecules are things that you want to have around if you want to form a living planet. Obviously, if you look at life here on Earth, that seems pretty reasonable. We depend on water, we depend on access to small organic molecules to sustain life here on Earth. But as astronomers are often accused of being too narrow-minded in trying to search for the same things to define habitable planets the same way. I mean, there's some justice to that criticism. And one of the answers that you might get is that, well, we can only look for the things we know to look for. If you don't have any hypothesis or idea of what to look for, I mean, you're not going to look at all, because you can't survey every single star and planet at every wavelength possible with a perfectly open mind. So you have to at least come up with some sort of idea or hypothesis what you're looking for. Now, the reason that astronomers and I would say people working with origins of life in general have focused on water and carbon or organic molecules It's not as Earth-centric as they might seem. Water, as we just heard, is incredibly abundant. It is a very excellent solvent for having chemical reactions in it. And carbon is quite unique in how many different kinds of molecules that you can form with it and just the chemical complexity you can develop with it. So if you're going to pick something to focus on, this makes sense. Doesn't mean we have ruled out every other possible scenario, but this is where we're spending most of our effort, thinking about planets that could fulfill this criteria. So how often are temperate planets hospitable to life? To answer that question, when we can't look at the planets directly, we go to try to observe the places where these planets form. As I said in the introduction, planets form in disks made of dust of gas around young stars. So this is an artist impression from a few years back of what these disks might look like. And I think it's reasonable to imagine that the kind of molecules you have in these disks, those are going to determine what kind of molecules you end up with on your young planets. If you have water in the disk, you will get water on your planet. If you have organics here, you will get organics on the surface of your planet. So if these disks turn out to, in general, to be rich in the kind of molecules that we're interested in from an origins of life point of view, that's a very good sign that we are, looking for the right things once we get to the exoplanets. Now, astronomers are exceedingly fortunate in that we have a new tool to study these disks that's just a few years old. It's called ALMA. So this is an aerial shot of a part of this telescope. So you can see this telescope consists of many different dishes that are sort of clustered together. It's in the Atacama Desert in Chile because you really have fantastic observing conditions there. And this, the fact that instead of building one big telescope, you build all these little dishes, that means that we can get a much better spatial resolution than you would otherwise. So typically, if you think about what's the best spatial resolution that you can get in an astronomical observation, it depends on the size of your telescope. The bigger the telescope, the smaller details you can see. But there is some limit to how big of a telescope you can build. And that limit is much, much smaller than the 10-kilometer distance that you can place these dishes. And the trick that astronomers have learned is that if you build two small telescopes and put them some distance apart, you can basically see the same detail as if you built the telescopes that's the same size of that distance. Now, with this telescope, I said we can study these disks. These are actual images of these planet-forming disks. They are, this is a compilation from 2 recently submitted papers. What you can see is that these disks are not smooth. There are lanes, rings in them. One of the main hypotheses is that these sort of dirts that are like lanes that you see in these disks, where there's missing material, that's planets being formed right now, carving out that material. So what you're seeing here, you're catching planets being formed as they are forming. Now, so this is right now I'm just showing you images, but I do want to explain what it is that you're actually seeing. So let's take a step back. Now, if you have a disk of material around a young star, you will see emission that is pretty smooth over different colors or wavelengths. That's because this emission is it's just heat emission. It's thermal emission. So if you sum up all the emission that you get from one of these disks, you will get one of the images that I just showed you. Where you have brighter emission, you have either hotter material or more material. So you get the more thermal emission, the higher temperature you have, and the more material you have. So towards the center of these disks is where you have the most emission coming from. Now, if you look in detail at the light coming from these disks, you will see that there are very narrow lines of lighter intensity that's spread out across different colors and wavelengths. These are there because molecules and atoms interact with light, not in this sort of smooth way that you get thermal emission, but in a quantized way. So a specific molecule, such as formaldehyde as shown here, will only emit light at very specific wavelengths or colors. Because of this, we can make images that shows where molecules are in these disks. So what you see here is one image of just the total distribution of the dust, which is a beautiful image. And then you see kind of a uglier image of where the formaldehyde is. It's not the formaldehyde's fault. When we take the thermal emission, we have tons of photons to collect, right? We have that whole distribution. When we take a single molecule, we have this very narrow wavelength of light that we can, add up together. So you get not this beautiful of an image, but what we can already see is that these images are not the same. So while the image of the sort of the total distribution of material peaks towards the center, you have a big gaping hole in the case of this molecule formaldehyde. So these kind of observations, it's what we use to assess what is the environment that exoplanets or proto-exoplanets are forming in. So let's go back to two things that we think were necessary for forming planets conducive to origins of life. That is water and small organic molecules. Let's start with water. So with water, we don't have beautiful images as the one I showed. We just have spectra. The important thing is that water is extremely abundant everywhere, almost everywhere in space, including in these disks around young stars. So what's shown in these two images is one spectra of gas phase water, so lots of water vapor if you are close to the star in these disks. And then the other image shows spectra of water ice. Means that there's lots of water ice if you're a bit further out in these disks. One thing that we would like to understand better is where you have this transition between water vapor and water ice in these disks. We have some idea on how you do it because we have tested it out on other molecules. So other molecules that were common in the comets were carbon dioxide and carbon monoxide. So just as water exists both as vapor and ice, those molecules should exist as vapor and ice as well. And we can look at those transitions in disks. So things to keep in mind, in these disks, they're surrounding a hot star, right? So if you're close to a star, it's hot. If you go further away, it gets colder. That means that for any compound, molecule, species you can think of, there will be a distance from the star where that compound goes from being mainly in the gas phase to condensing out to be mainly present as an ice. We call them snowlines. So water is the one we would like to know the most, but we would like to know them for pretty much any species or molecule in these disks. The one we have managed to take actual images of is carbon monoxide. So what's shown here is an ALMA image of this transition happening between CO ice and CO gas. So where you see this green fuzziness, that's where in this disk you have CO ice, and the hole in the middle is where you have CO gas. So these are things we're hoping to be able to measure also with water in the near future. Now, the way that we measure this, so I want to go in a little bit on the science of how we actually measure these transition regions, is illustrated here. So this is a cross-section of one of these disks. I just cut it in half, and I'm just showing one of the sides. So closer to the star, it's hotter. Also, if you go higher up in the disk, it's hotter because you're exposed to the stellar light. And then you have this region in the middle, going a little bit further out in the disk, where it's very cold. And that's where you're going to have ices, in this case, CO ice. Now, we wish we could image this CO ice directly, but we can't. All we can do with ALMA is look at what's in the gas. That is like one of the big limitations with basically all the observations we do, is that we can only see whatever is in the gas in these disks. So instead of what we do is that we take advantage of that there are molecules that only show up when you have CO ice. And one of the molecules that only shows up is this weird ion which is a nitrogen molecule with a proton attached to it. So it's N2H plus up there. Basically nitrogen with a proton. Now the reason that this weird ion only shows up when you have CO ice is that as long as you have CO gas, this ion is immediately destroyed. Molecular nitrogen and carbon monoxide basically compete for that proton. So as long as you have CO and the carbon monoxide in the gas phase, that proton will be stripped off the nitrogen molecule in no time. But if you're in a region where all the CO has condensed out as ice, that ion, N2H plus, becomes pretty long-lived, and we can detect it with ALMA. So that's sort of the trick we play in measuring where these transition regions are, and we're working on doing the same with water. But no matter whether water is in the vapor phase or in ice phase, we know that it is abundant where planets are forming, and we don't really think that access to water is going to be a limiting factor when making habitable planets. I think that is something that there's quite some consensus about. So how about the second thing, the organic molecules? Are those abundant in these disks as well? Well, at least we are detecting them. So this is a small compilation of the organic molecules that we have observed in these disks using this telescope ALMA. So you can see that there are hydrocarbons, there are nitrogen-bearing organic molecules, and there are oxygen-bearing organic molecules. So basically the major families that we would be looking for. Now if we take just one of these molecules, and I'm going to take formaldehyde, so the smallest oxygen-bearing organic, and we take images of how this molecule is distributed in the disks around different stars, we get images like this. So what we have are, so these are 12 different disks around 12 different young stars, and it's just showing where the formaldehyde is at in these disks. The thing to notice is that excellent question. So it's the bright spots. So actually, let me do the color scheme. So brighter color means more formaldehyde. I mean, that's the key. So where there is black, you have either reached the edge of the disk, or for some chemical reason, you have lost your formaldehyde. Maybe it is has been converted to a different molecule. Maybe it's being destroyed by radiation. There's some reason that it's missing. So the thing to notice is that the formaldehyde distribution in these disks doesn't look the same in the different disks. Sometimes it's centrally peaked. Sometimes it looks like it's more in a ring. This diversity of distributions means that there is something local in these disks. There's some local conditions in these disks that's determining where the formaldehyde is at. Based on that, we would expect that you're going to develop different kinds of chemistries in different disks, and therefore potentially in different planets that are forming in these different disks. Also within the disks, you can see that in some places there's a black hole in the middle. That means there's a dearth of formaldehyde. Planets that form there would supposedly have less organic material than planets that are forming where you have these bright rings. So both between systems and within systems, we would expect planets to form with very different sort of chemical hospitalities to an ordinance of life. Now this becomes especially interesting if we ask our colleagues, our chemistry colleagues who are thinking about the chemistry of ordinance of life, if there are some molecules that are sort of especially interesting for the ordinance of life. It turns out that not all organics are equally important to sort of kickstart an ordinance of life chemistry as we understand it. I think the most successful chemistry so far to get us from basically bare bones kind of chemistry you can expect to have in space to the building blocks of life as we know it here on Earth starts with hydrogen cyanide, so HCN. If you have this molecule and you have UV light and a couple of other ingredients, you can pretty much form all the things that we associate with life as it is here on Earth. So it's amino acids, nucleotides, so what makes up RNA, DNA, membrane, like part of membranes and so on. So one could ask how often, so HCN, obviously not very good for life once it exists, but very good, as it turns out, to kickstart this chemistry. So what about this molecule? What about cyanides in disks? Well, the good news is that these HCN is very common in disks. So this shows 6 of the disks where it's detected. Again, brighter color means more HCN. So it's definitely there. Our solar system is in no way unique in having had quite a lot of HCN around at its infancy. Just as with formaldehyde, we can tell that there is an active chemistry in the disk that's forming and destroying this molecule. We have, there are multiple sort of signs of this, but the one that I like the most is the one that's illustrated here. So what's shown here is 6 different disks. So each column is its own system. And then the 2 rows are both hydrogen cyanide, but where you have replaced one of the atoms with a slightly heavier atom. So in the top row, we have replaced the normal carbon with carbon-13, so it's just slightly more massive, but otherwise it's the same. And in the lower panels, we have replaced the hydrogen with a deuterium, so it's basically heavy hydrogen cyanide. Now, if there was no chemistry going on, and that this hydrogen cyanide was basically just sitting there during the full epoch of planet formation, you would expect the top panel and the bottom panel to look identical. There would be no reason for these two to look different. But as you can hopefully see, even though these are not very high signal-to-noise images, but I'm going to guide your eye to the one where I think is the most obvious, these 2 types of hydrogen cyanide are not distributed the same way. One of them is very compact. One of them is sort of distributed over the full disk. We can understand this if there is an active chemistry going on. Remember, there is that competition between entropy and energy, which determines which kind of heaviness, let's say, of the molecule that you end up with. But we could not explain it if it was not an active chemistry going on.
How big is the size of the box?
Hundreds. There's I pretty much removed all the scales, so I guess it's a good time to clarify that. That if we look at our solar system out to sort of Pluto, the Kuiper belt, that's an order of 50 AU. These disks that I've shown you are sizes between 50 and 400 AU. So they vary a bit, but here they're all on the order of a couple of hundred AU. We don't just see this simplest cyanide, but we also see more complex cyanides. I mean, this is an artist's impression because the discovery image looked really ratty, but it's there. We see these more complex molecules. In the first disk we looked for it, we saw it. When we looked at a small sample of 6 disks, we see these more complex cyanides in sort of 3 to 5 out of the 6, which suggests that there is a really robust organic chemistry taking place in space that's producing the kind of molecules that we care about from an origins of life point of view. That would suggest further that the majority of planets will assemble in disks that have these right ingredients for the origins of life as we are currently believe it took place. However, and this is a big however, the distributions and the abundances do vary from system to system. They can vary by easily a factor of 10, a factor of 100. And since we don't know how important this source of hydrogen cyanide is for young planets, this is something that might matter and make some exoplanets much more conducive to an origins of life than others. So if we're to sort of sum up before getting into the last section. Based on direct observations of these disks around young stars, and this is another of our artist impressions, we know that they are rich in water. We know that they are rich in organic molecules of different kinds. Most especially, we're happy that they are rich in the cyanides that are currently the favorite precursor of the origins of life chemistry that we think happened on Earth and led up to us being here. However, there was that big however, that they're not always as abundant. And they're not always distributed the same way, which might play a big role for actually delivering some of those molecules and how much molecules to deliver to the nascent planets. But there is one big sort of obstacle or puzzle that I've so far swept under the rug that I now want to reveal to you, I guess, so where we're heading next. And that is the following. All the observations that I have shown you so far are of molecules that are in the gas. They're of vapor, of organic vapor, water vapor, what have you. But in these disks, most of the material is actually found in the cold parts of the disks where things are frozen out, where you have ices rather than gas. That ice is just invisible to the kind of observations that I just showed you. Now there are ways, like moving forward, one of our sort of main goals is to use those gas observations that I showed you to infer what is going on in this blue circle, where most of the material is, and indeed most of the planets are actually forming. And there are two ways that we're going about that. One is to take into account that these planets, they don't just appear out of nowhere. They have a history. They form through the collapse of clouds in the interstellar medium. This formation is rather violent. And as part of this formation, you will see the sublimation of some of those ices and can therefore characterize them. So that's what's shown here. The other is that we can construct laboratory experiments that really simulate what happens in these ices and in the gas in the disks. And that's just what I want to talk about for a few minutes, how we're using those laboratory experiments to predict both what's going on in the midplanes of these disks and how that ice chemistry manifests itself in the gas that we can actually observe. So what we have as a sort of model framework, and that has been around for about 30 years or so, for how most organic molecules form in space is the following. I said in space you have gas and you have dust. So this is an interstellar dust grain. This is what eventually will coagulate to form bigger and bigger pebbles, boulders, and planets. But they're there from the beginning. They're about a micron or so in size, a little bit smaller. Now, when these grains are cold, let's say 20 degrees above the absolute zero, anything that touches the grain will stick to it, including molecules that we typically think about as gases, like carbon monoxide. So what's shown here is the carbon monoxide condensing out on the grain, and then you have hydrogen atoms attaching itself to the carbon monoxide molecule, and you get a methanol molecule, so the smallest alcohol. So that's how you get sort of the smallest organic molecules. Now, if you then have some radiation around, some UV, some X-rays, some electrons, you can break apart that initial generation of organic molecules. And once you break things apart, they can react to form larger molecules. And this is something that we can test in the lab, just how efficient that is. And I'm going to basically show you what happens if you take methanol ice in the laboratory and you start irradiating it with UV light. So the first thing you do is just you start breaking it apart in any possible way you can. Turns out nature is rather agnostic with how you break apart this methanol molecule and other small organic molecules. And even if you are sitting at the very low temperatures, we're talking about maybe 20 degrees above the absolute zero, these now fragments of a molecule can move around if they have long enough time and recombine to form larger organic molecules. So this shows what happens with sort of the first generation afterwards. You can imagine you can then dissociate the next generation of molecules and have them recombine into larger and larger molecules. And if we do look at this earlier, more violent stage of star and planet formation, we do indeed see a lot of very complex molecules right where these ices are sublimating off the grain. So this shows, this is a press release image of the first chiral molecules that were detected in space. We don't know if there are any excesses between the left-handed and right-handed molecule. I think the most important thing is that we actually see molecules that are big enough that they do have this chiral center, or they're big enough they can have mirror images that are not the same. So to start wrapping up, whether we're trying to understand our own origins, we're back looking at our Earth and understanding why we have this one living planet in what otherwise seems like a rather dead solar system. I mean, I'm still hoping we're going to go and drill down into Enceladus and find that there are some bacteria there, but at least so far we have not found life anywhere else. Whether we're trying to understand this, or whether we're trying to understand how often how many other living planets there might be out there, my suggestion is that a very good place to start is understanding how these planets form and what their environments are like when they form. And what's been so amazing in the past sort of really 2, 3, maybe 4 years is that we do have this new telescope, ALMA, that allows not just to take images of what these disks look like physically, so where the material is in these disks, where planets might be forming right now in these disks, but also how different molecules are distributed in these disks. So this is just one of those disks that are shown in the previous slide, but instead of showing where the dust, where the material is, it's showing where one of these molecules are that we're interested in. And one of the things that we see is that when we look at different disks, the chemistry is not the same, but maybe most interestingly, within these disks, we do see like rings, gaps, sometimes we look some asymmetries, suggesting that planets, comets, other bodies that form in these disks, it really matters where they form. You're not going to form the same planet, even if it's the same size, if it is at 1 AU, 10 AU, or 100 AU. You will end up with very, very different planets. So with that, we are, where we stand right now is that, as far as we can tell from studying these disks, and from the theory of how planets form, is that the access of water and sort of feedstock organics, these small organics, for young planets, that really depends on where they form, how they form, and the environment in which they form. The environment in which they form are these disks of dust and gas around young stars, which we now can study. And what these studies reveal is that these disks are generally chemically very rich. You do have the same kind of molecules in these disks as we do see in comets. And some of those molecules happen to be exactly those molecules that origins of life chemists are looking for to have on their planets. So that's the good news. I mean, at least, well, I guess good news if you, like I, hope that there are other living planets out there, this will be good news. If you belong to a slightly more nervous or anxious kind, this might be less good news. But if this is part of what you hope for, this is good news. However, as I've said several times, it's not obvious that they're all the same or all as conducive to this pre-life chemistry as the solar system were. This is for 2 reasons. One is that we don't know how life originated here on Earth. We have ideas. There are theories that are being explored right now, and obviously the collaboration here is a big part of that effort. And because we don't know, even if we are right about the general scenario where this hydrogen cyanide is at the center, we don't know how much it matters whether you have a lot or a little. Maybe having just 1% of what we had here on Earth is sufficient, or maybe we were sort of in the lower range of what's needed to kickstart this chemistry. That's something that we just don't know. And then seeing this variability means that we have to have an open mind on that. Not all these systems, maybe not even a majority of these systems, may be as hospitable to life as our solar system was. But I do think it is very promising that whether we look at different places in space or whether we try to simulate things in the lab, forming many of these organic molecules appears to be very easy. There's a very sort of robust pathway to forming these molecules in space. And it might be that actually some of these variations that we see in abundances of things like hydrogen cyanide might actually not be true variations. They might just be differences in how the ice and the gas are communicating in those systems. And understanding that better is definitely one of the big things that we're trying to get to as moving forward. And before ending, I just want to make a point that the kind of results that I presented, obviously not all of them were from my group, but some of them were. And that what we rely on is having a lot of young, smart, enthusiastic scientists doing the work. I think almost everything I presented, maybe with like the exception of one slide, was done by was led by a junior scientist, and many of them are pictured here. So without those and without the support, especially of the Simons Foundation, this work would not be possible. So I'm very grateful both for the team and for the support I'm getting from the foundation. And with that, I'm happy to take any questions.